Well, we're going to go ahead and begin today's seminar. So welcome everyone to the first ME department seminar of the year. We're lucky to have a distinguished speaker here today who also happens to be a really, really nice person.
Reading
Known
a
Alissa
new
for a long
circular
time.
carbon economy.
We have shared interest in the American Chemical Society and the Energy and Fuels Division in particular. So it's great to see her here. Alissa Park is a distinguished scholar. She also now is the Dean of the College of Engineering at University of California, Los Angeles. She's been here since 2023. Prior to that, she was at Columbia starting in 2017 and spent 2.5 years as the chair of the Department of Earth and Environmental Engineering. She's received a number of awards recognizing her distinguished scholarship. She's a fellow of the AICHE, the ACS, CIFAR, the Royal Society of Chemistry, and AAAS. She's also, and I'm very impressed with this, that she's won the C3E Research Award. I've nominated someone for a C3E award unsuccessfully. I know how much competition is. If you're not familiar with C3E, that's Clean Energy Education and Empowerment. And it's meant to recognize outstanding female researchers, scientists, and educators. So we're delighted to have Alissa here. I'll just say she has her bachelor's degree from the University of British Columbia, lovely place. And she has a doctorate from Ohio State, but don't hold that against her.
I know.
Professor Park.
Thank you, Andre. Very nice to meet all of you. And in fact, I was at the ACS meeting, and for Chris Jones, we were having, I think he got the Murphy Award. So we were celebrating his, and he was raised in Michigan. I don't remember whether he went to undergrad here, but anyway, there's a lot of Michigan connection. And then he asked the question to one of the guys from Ohio State, how many days it has been since we lost, right? I think it was many, many thousands days, I think. So we were like, we don't talk about that. But very nice to be here. So as he mentioned, but one correction, I started at Columbia 2007, not 2017.
2007.
Yeah, but I was chair only for 2 years. So maybe that's what you were looking at. But yeah, it's been around. I'm not as young as I hope. Today, I would like to talk to you about the carbon management. And it's nice because I always had a connection with, I'm an external member, right? CO2 Global Initiative. And then we tried to get ERC twice. And I met some of the buddies who wrote those proposals last few times. So eventually we'll get it one day, right? But it's been kind of interesting 6 months, I think. So I think I'm being recorded, so I'll be very nice about the situation. But we can have open discussion about what's happening in terms of climate change and all that so on. So here, let me see. It's not moving. Come on. Oh, my computer is kind of frozen. How about you? No, it's not.
There you go.
Now it's working. All right. So I'm not going to talk about carbon dioxide concentration in the atmosphere. We saw a lot of these photos about climate change. Let's not talk about that since we already agreed, right? Despite of what others are saying. But having said that, this carbon capture and storage or utilization research started even before my time as a graduate student. So it was about 30 years ago in the United States. I think a lot of people started thinking about what do we do with the carbon emission? And that was even before the time thinking about sustainable energy. We didn't even have a term sustainability at the time then. But when you think about new technologies in large scale, I'm a chemical engineer by training, and normally you say from the bench top when you come up with the new materials, new chemical reactions, commercialization to all the way to full scale, about 20 years. That's a rule of thumb, right? So then about 2013 and 2014, that was about time we've been working at carbon capture about 20 years. So it was the right timing for people to start asking questions. We gave you 20 years. What happened? Where's the carbon capture technology? So people in our field start to panic a little bit. Oh no, we had 20 years. So what happened? We don't have fully commercialized carbon capture technology. But then, so we were really worried. But instead of shutting us down, they were saying that, well, this is an even bigger problem. So that when you talk about the zero emission in power plant, it's a smaller sector of the whole thing. So you have some positive emission in the power plant, burning coal or natural gas, and we want to do carbon capture to zero emission. That's one. But then they were saying about 2013 or 14, almost a little over 10 years ago, they said that not only we have to go to zero emission, we need to go to negative emission technologies. This is a big deal, right? Because not only what is being emitted, we're going to capture and do something about it. Now you need to go back into history and pick up the carbon we emitted decades ago and do something about it. Huge challenge. So with that, a lot happened last many years. And in fact, the last Biden administration was so serious, and they're far beyond just doing decarbonization of the power sector. And they were very interested in hard to decarbonize industrial sectors, such as the steel industry, cement industry, and all those things a lot of you are working on. So they were so serious that they changed the name of office within Department of Energy, where a lot of our funding on carbon management came from. So instead of having Office of Fossil Energy, I think they tried to scrub the whole thing and then come up with the whole entire office. They weren't successful, so they just added carbon management. So now we call it, instead of FE, we have FECM. Hopefully they will survive. So then not only they changed the office name, which is kind of telling you that initial time, like 30 years ago, a lot of us, well, not me, a lot of researchers thought carbon management technology, CCUS, carbon capture, utilization, and storage is a bridge technology. We'll get there. It'll be a short bridge. We need to cross until we get to clean energy transition. But now people start to realize this is a long bridge. Not only that, it's not, even if we have a clean energy transition completely, we still have to manage carbon in both natural and engineered systems. And I think that's where it came about, that this is the long haul, and this is a whole new way of looking at our resources, and not only energy, but also material resources. Last government was very excited about this whole picture. So the overall goal was, can we get to net zero economy by 2050? That's very different from zero emission at power plants. That's easier goal. This is a huge daunting goal by 2050. In order to get there, they start doing something called energy earthshot. So this is one of the energy earthshot, which is the first one came out, which was mid 2021. It's been a while, about 4 years or so. And I think some of you are working on this, right? Hydrogen. So it was all about hydrogen and how to make $1 per kilogram of hydrogen in 10 years. It's really challenging because it's really depending on what is the price of hydrogen today. Does anyone know?
$20 to $30 a kilogram, depending on where you are.
That's quite often carbon-free one, right? So there's a dirty hydrogen, right? So if you have really dirty one, it would be much cheaper. Even then, I would say $2, $3 per kilo. But if you say, like Andrea is saying, it's a kilogram of hydrogen, which is carbon-free, very expensive. So it's a long way to go. There was a third one, Energy Earthshot, was all about carbon. And it came out late 2021. It was, can we do carbon management, capture, transportation, storage, or utilization, whole value chain at $100 per ton of CO2? Still very, very daunting task. So cheapest, or one of the cheapest way of capturing carbon is from power plants. Right now, the cost will be $40 to $60 per ton of CO2. That's that number being thrown around about 10 plus years. So I'm guessing this is much harder still. So let's think about, how do we capture carbon? And this is where we started. So when you think about CO2, I'm going to try to minimize the chemistry discussion, but CO2 is acidic gas, weak acid. In order to capture it chemically, you need a base. It's an acid-base reaction. In fact, climate change challenge, especially based on CO2, is all about acid-base reactions. So in order to catch weak acid, we need a base, so which is like amine liquid solvents. So the reactors over here, you have most of the separation techniques, not only just looking at carbon capture, anything. The separation technology is usually catch and release, because you're not going to catch and then throw the whole thing out, right? The materials we need to recycle back and forth. So green one, basically in this figure, is the catch reactor. CO2 capture reactor, if it is power plant, usually 40 to 60 degrees Celsius. And then once you catch, it's usually downhill reaction. So stronger the binding energy, green reactor will love it, right? Reaction will go fast and much faster and very selective. But then you pay for it in the red reactor. because you need to put energy in to release that CO2. So people are debating what is the right binding energy. It should be strong enough, but not too strong. Because if it is too strong, now you need to put energy in here in terms of either heat or vacuum at such high level, it's not going to be economically feasible. So amine was something in between that's strong enough to bind, but is enough to release at 120 to 160 degree, 40 degrees C, which is around the temperature we can still use waste heat to release. That's why there was a forward concept of it. So after studying for many, many years, finally 2016 in the United States, we start to scale up, much larger scale. This is near Houston called Petronova project in one of the power plant. And people done quite a bit, and you need to learn so much about the scaling up before we can really commercialize. So while we're working on this, people start to say, well, it's still very expensive. Why is it so expensive? There are many different reasons. One of the reasons they didn't anticipate was that these amine-based liquid solvents degrades much faster than people thought. So for new research area, which I'm not going to talk about today due to the time, is that how to make amine solvent last longer by improving their oxidative thermal stability. But at the same time, liquid solvents, usually amine, you can't use it as a pure form. So you need to kind of dilute it in water. So most of the liquid solvent is about 15 to maximum 30 weight percent amine. So you have 70 to 85% water coming along the ride. Remember I was telling you catch, release, at lower temperature, high temperature. So you're basically heating up all that water and cooling it down. Heating all that water, cooling it down very fast. This is not an easy task. So because of that, what they were saying was, if we do something like this in the power plant alone, you'll reduce the power plant efficiency by 1/3. That's a huge hit. So they start wondering, like, why? Like, can we reduce that energy? I think at the end of the day, if you ask me today, I want to build a CO2 capture unit full scale, I'll say do this. Just because we know so much about this material, we know how to design the process at that scale. But if we can kind of try to think about innovative material to capture CO2, the second generation of liquid CO2 capture solvent was water lean, waterless. Just get rid of all that water and let's keep as much amine as possible. So the materials I worked on at Columbia was something called NOMS. NOMS is nanoparticle organic hybrid materials. In fact, the first generation of this material was developed by Lyndon Archer, the polymer guy at Cornell. Very nice guy I worked with. And basically he tethered the polymer onto nanoparticles. And the final product was very interesting. Instead of powder with coating on it, because we did the right grafting density and it's short brush, you end up with this liquid-like material. In your bottle, it is still liquid. It flows and all that. And the reason I really like this design for carbon capture was I really wanted to increase as much free volume as possible. So the tethering of this polymer onto nanoparticle was done with the right grafting density, right size, right conformations to maximize the free volume between polymer chains so that I can jam pack as much CO2 as possible. And I was hoping that this will behave something similar to ionic liquid, which has almost zero vapor pressure. So you can increase the temperature to 100 degrees C. Hopefully there's no fume coming out, which is one of the ways you lose a lot of your liquid solvents. So from there, we wanted to see whether it does change the structure of a polymer as you tether them. This is just a simple 2D ROSI NMR data. So if you are not familiar, left and right, there's a very big difference between signals, right? Because this is untethered polymer. This is after we make NOMS by tethering them. Basically, what this signal is telling you that polymer I tether onto nanoparticle were stretched out from each other. So they're creating indirect method showing that there's a lot more free volume we created. So next thing we really checked was, is it really robust through many thermal cycles? Because these materials should last thousands and thousands of cycles. So if you look at left figure that I should use, walking around too much. Here. So here, this is a great degradation of untethered polymer as you tether them, it gets much more robust. I'm not going to be able to talk about why this is as robust, especially if it is under oxidative condition. This is very robust. And in fact, this lasts 100 cycles, and I was a nice professor to stop the reaction then. My students would stop at 100 cycles. Compared to untethered polymer, it degraded almost to nothing. So one of the reasons I found out was that liquid we made, we tried to remove the water as much as possible because it's supposed to be water-free liquid solvents. And then what we found out was a 3 to 5 weight% of water you cannot ever get rid of. You can pull a lot of vacuum, you can heat it up, they were stuck, it won't come out. So then I'm like, okay, this is dead weight, water weight. I need to carry around back and forth in different reactors. What we found out was, in fact, those water were stuck in between polymer chains. This is drawn with CO2, but water was in between polymer chains. So what happened was CO2 can penetrate through that layer easily and get to the amine functional groups. At the same time, oxygen did not like the water, it was staying outside. And because of that, we were able to protect all these amine functional groups. Anyway, with a long story like that, now only thing we had to do was we just need to put a lot of amine functional groups, which we did, and as we expected, it really improved the total CO2 capture capacity, but it was expected. So we got really excited. I'm squeezing like 7-8 years of research into few slides, right? So then I started thinking that, well, it's getting really exciting in terms of CO2 capture capacity, and it's a really robust material, selectivity is excellent. Now we just need to put it into huge reactors. At this point, we were still making tiny microliter of this material, doing all the fun stuff. So then my student asked me, oh, so we need to put this in the reactor? And if you look at the little bottle we have of gnomes, if you flip it, it goes, it doesn't free flow. It's really highly viscous material. If you look at second generation CO2 capture liquid solvent, water lean and waterless, or high viscosity. Ionic liquid is high viscosity, gnomes is high viscosity, many of these are high viscosity, and that's why almost near vapor pressure. So good and bad at the same time. So a lot of my friends, like here, this is the data showing that this is the viscosity, functional temperature. These are the amine-based liquid solvents. It looks like water. Very easy to design a reactor. You can do spray tower, trickle bed, many different designs you can do. Mass and heat transfer, very easy. There are some of the examples of ionic liquid. These are our gnomes material. So our friends, including John Brannicky at UT Austin now, she said, we can reduce the viscosity to maybe 20 or 40 centipoise. And she's done it by changing the hydrogen bonding network. In fact, we can do something similar with gnomes and bring down viscosity. But I looked at this and got sad first, and I looked at it again, I got really sad. Students, do you know why I got depressed after looking at this slide? The results? This is not linear plot, it's log. You should be depressed, right? I'm like, oh no, this is not non-linear, it's log plot. So this is a huge orders of magnitude high. It's very viscous. So why do we care about viscosity? Because heat and mass transfer is very difficult, challenged. And also that creating interfacial area between liquid and gas would be very hard. So then I started thinking about this for a while. And then there's no way we're going to bring this viscosity down to here or even here. So we started thinking that, well, can we create a lot of interfacial area, still benefiting from almost a negligible vapor pressure and all that. So then that was about time my friends at Lawrence Livermore National Lab, Roger Ains group, started doing, they were encapsulating salty solution. That was one of the CO2 capture technology. They were doing dissolution, crystallization, dissolution, and crystallization of salt solution in encapsulated system. I thought that was really interesting. So I thought, well, our sticky honey-like material, if we can chop them apart and keep them apart, maybe this was the thing. So we start working with them on microfluidic device, and now we have a whole another system doing this. The blue, we just put the blue dye so we know where our material is. And clear liquid here is a UV curable polymer. So you have a microfluidic device making droplet instead of droplet. And then we UV cure, only curing the shell material, which is porous to CO2. And then this porous material, now you have combination of this is a liquid solvent still inside, intact, with a large surface area per unit volume, with the shell material letting gas in and out. And because our material has a zero vapor pressure, near zero, that it won't evaporate, even if you put these particles outside. This is kind of interesting way of marrying the liquid solvent benefit with solid sorbent benefit into one package. So here's some of the materials we actually made. This is a multi-core, single core. In the naked eye, if you hold it in your hand, it just looked like particles with the stuff inside. And then it really worked really well. So here, this is the gnomes without encapsulation. And as soon as you encapsulate just pure providing more interfacial area, we were able to capture much faster. So this was our earlier work. And then start thinking about what would you do once you capture CO2? You need to do something. You're not going to catch and release back to the atmosphere. And in fact, if you care about climate change, that's the reason you're doing this, we have to store. Because there's only so much conversion you can do, but you need to store, and we cannot build large enough storage tank to store all the CO2. So you kind of have to go to Earth systems where there's a lot of porosity. That's how we get natural gas, right? Once you get all the natural gas out and oil out, there's a lot of pore spaces we can put our carbon dioxide. This is very famous schematic diagram from Sally Benson at Stanford. And she said that if you inject 150 atmospheric pressure pure CO2 underground, which is supercritical CO2, this is what's going to happen. First, there will be a cap rock so that it stays as a 150 atmosphere high pressure CO2 plume, and it slowly goes into the pores, replacing whatever is in the pores. And then if there's water, you start to dissolve into that water system and start to depressurize. And only if there's a mineral which can react, you start to make something like limestone. So this is a kind of 4-step. And the good thing about this is that once you make the carbonate, this is one of the very few downhill reaction, as you can see. So from coal to natural gas to CO2, and then one more downhill making limestone. So unless you burn limestone at higher temperature, you're not going to get that CO2 back. This is a natural way of storing carbon dioxide CO2 for long term. So again, students, there's something missing on this scheme. What's missing?
The date.
Yes, there's no number, right? It could be a year, it could be 100 years, it could be a million years, who knows, right? So people are debating over how fast, slow this process is. And most of the time, people thought it would take really long time. And it does take a long time, but one particular case in Iceland, they actually was able to inject CO2 and convert that into solid carbonate less than 2 years. Really depending on the site. And in fact, they did not inject the supercritical CO2. They bypassed these 2 steps, went to all the way here. They just injected carbonated water. And then saw how fast this reaction was, which they thought it was slow, but they were able to show that it was only few years. So depending on the location, maybe we can do this much more safely. But today, I'd like to talk to you more about this side, utilization. Here, there was a very interesting paper came out from McKinsey 2020. Oh my goodness, it's already 5 years in, right? They were projecting only 10 years out. They said by 2030, this is how much CO2 storage and CO2 utilization potential they guessed. This was their estimation. And this light gray bubble is how much storage they thought we're going to be doing by 2030. We only have 5 years left. And I hope that it will be underestimated number for our climate change mitigation. Bigger the light gray bubble is better for us. But the part really surprised me was blood bubbles. Look at the blood bubble. They said that by 2030, you will be making fuels, construction materials, even plastics and chemicals from captured carbon dioxide. I thought it was a big estimation. Economics, is it going to work out by 2030? I don't think so. But they thought that there are so many drivers, policy and other market drivers that drives all these creating this market by 2030. It's really interesting. So let's look at this picture in New York City and some of the chemicals. Maybe you used some of these chemicals this morning taking shower, or used it around even looking at this carpet here in this room. I'm sure this carpet came from petroleum product, cheap polymers, right? So that Can I decarbonize this room? Can we? Yeah, maybe some of you work on biomaterials, right? So that if we get biopolymer and convert this from the petroleum-based polymer carpet, I'm sure we lower the carbon footprint or getting very close to hopefully net zero, right? Carbon neutrality. Can I really completely get rid of all the carbon in this room? We can, but we need to work over too, right? We're carbon too. So what I'm saying is that in order to really get to net zero economy, this is very hard because not only we need to do decarbonization, but we need to do something called defossilization. We still need carbon, but can we use non-fossil carbon to create everything you use, everything you see, everything you burn or use as an energy source? So we had a lot of discussion, including the Global CO2 Initiative, on how to create a whole new circular carbon economy. But at the end of the day, next 10 years or so, we may not be able to create a whole new commodity chemicals for the future. The way we make, what chemicals and materials and fuels we make and use might not change so much within the next 5-10 years. But hopefully we'll be able to start picking up carbon from the environment, and only input to this circular economy should be renewable energy. And if you're doing CO2, there's only carbon and oxygen, you need hydrogen to make stuff. So that we need hydrogen, and we'll have to learn somehow how to capture carbon from a wide range of sources and convert it. But one thing you have to remember, I'm telling you, entire system has to be net zero economy. That's a huge scale. So that from the day one, it's not niche market, that you need to think about tech to market from day one. We don't want to be the one and say, oh, we developed all this technology, but there's no way we can replace all the commodity chemical using this whole new circular carbon economy. Because of that, we need to think about economics and policy as well. Okay. Today, I'm not going to have time, but there's one thing people miss quite a bit when we talk about circular carbon economy is hydrogen. Where would you get that hydrogen, right? There's a whole another seminar we can give, but this hydrogen apparently now has color, right? Andre, what is your favorite color? Hydrogen.
Green.
Green. Sure. Green is our lovely color. There's a blue hydrogen, pink, and now the latest one is white and orange. So color coordination is based on what is the carbon intensity of that hydrogen. So you need to choose the right hydrogen color, otherwise the whole circular carbon economy is not going to be carbon neutral at all, because the carbon intensity is linked to hydrogen. So I'm not going to talk about that, but let's talk about carbon again. So the entire commodity chemicals and materials, if you need to you need to use non-fossil carbon. It's a huge amount of carbon we need to get, right? Somewhere. So then we have to look into environment. Where is the carbon? So being an engineer, I made into very, very simple question. Let's think about what is the biggest body of gas, liquid, and solid. So what is the biggest body of gas? Entire atmosphere, right? What is biggest body of liquid? It's shown very tiny here, but ocean, right? So ocean and sea, like the rivers and lakes and all those things. And biggest body of solids will be all the rocks, mountains, and dirt and all that. As I told you, most of the carbon in solid rocks, unless you burn them, it doesn't come out. So maybe don't touch that one. Maybe it's good to leave them as it is. But there's an equilibrium between atmosphere and the ocean water, right, seawater, so that if you tap into one, you'll be changing the other anyway. So you can do either direct ocean capture or direct air capture. Either way, it's all connected to each other. Or you can do it either chemically, physically here, or you can go through biomass, which many of you are working on. So you can do terrestrial or marine biomass, and that's another way to tap into non-fossil carbon. So today I'd like to talk to you a little bit about direct air capture. How can you even capture CO2 directly from air? I just told you, even installing carbon capture technology in a power plant with 15 volume % or 7, depending on what you're burning, is challenged. So if you're going to 400 ppm, or today maybe 420 ppm parts per million CO2, is it easy? Definitely not. You're right. So it's not easy, and challenges are very different. So this is the picture I took at Climeworks in Switzerland. So this is one of the their direct air capture system. Historically, if you remember the picture I showed you about Petronova project, it's a huge system. So we were counting on economics of scale by making bigger and bigger and bigger to lower the price. Direct air capture is a little different. What they did is instead of scale up, they did scale out. Basically copy paste, many of them in modular design. So in fact, the one unit is about my height, I think, is like a square thing, right? So then this not gonna have economics of scale, but what they're gaining is faster learning curve. Because each year, when they make a new version of it, it'll be much better. So for example, you're not gonna use the 10-year-old laptop, right? Because it improves every year. But if you're doing economics of scale, you cannot build power plant every year. So learning curve is very slow. So you get one or the other benefit. In this case, they took the faster learning curve. Issue with this is that we are dealing with only 400 ppm parts per million of CO2, and because of that, there's no way we're going to go down to 95% plus CO2 capture. So generally, if you can scrub out more than 60% of CO2 from incoming air, you're good. That's the target. And there are other challenges. You need to process so much air, ambient air, to get 1 ton of CO2. So if you have a high pressure drop in your system, you'll be paying so much energy into that. Whatever design you have in your system, you should have a minimum pressure drop for sure. And you need to deal with the high oxygen concentration in the air, remember 21%, but the problem is that most of the materials to capture CO2 is really prone to oxidative degradation. And another challenge, as you can see, incoming air fluctuates. Some days are dry, some days are rainy, some days are cold, some days are hot. Or even during the same day, you can change the temperature and pressure and weather condition like crazy. So it's really hard to run anything steady state, isothermal, all these are very big challenge. So it's a kind of interesting way of designing a reactor, including the environment in your system boundary. So I was looking at that, and the reason I was excited was my material. Remember, our gnomes material has a 0 vapor pressure. So if I have a cup of gnomes and sitting outside, then what happens is that it will collect the CO2 slowly because it's high viscosity, but it won't evaporate. For years and years, it will sit there, but it's very sticky. It collects a lot of dust, which I didn't want either, and I need a lot of interfacial area. So then I started thinking that instead of making that encapsulated particle, I wanted to have a low pressure drop. So we started thinking about how about electrospun fibers. So my friend at Cornell, Young-Ju, he actually did a lot of electrospinning of fibers for fuel cell application. So I said, okay, how about Young, can you make this material with my gnomes material stays inside, not outside, because it would be very sticky, and then it collects a lot of water as well. But my friend Misha Kidder at Oak Ridge National Lab, Andrea knows very well, she was making this PIM material, which is polymer with really, really good frost. So that I wanted to PIM to be outside, gnomes to be inside, make a electrospun fiber, looks like this, so that we can control the overall pressure drop to be very low. And we were able to actually do it. It was DOE funding. And these are the picture of some of the fibers. And as we expected, this is just the gnomes, and this is a fiber encapsulated gnomes capturing CO2 very, very fast. So we actually tested many different polymers too. These are 2 examples. There's a PI, one of the popular amine-based polymers, is a branched one. Compared to TIPA, is much shorter amine functional group polymers. And when we looked at that, one of the things I wanted to do was by putting PIMS outside, PIMS is very hydrophobic. So if we can, or most of the materials love CO2, also loves water. So if we can minimize picking up water while capturing CO2, that's fantastic. So I wanted to design this fiber material, selectively reject the water while letting CO2 in. So hydrophobicity on the surface of this fiber was very important. So as you can see here, when you have PEI, even just regular PEI or gnomes encapsulated in this PIM, still hydrophobicity is good, especially gnome-based ones are fantastically hydrophobic. But TIPA is so tiny that it migrates to the surface and you don't have like a hydrophilic surface now. Okay, CO2 capture in the direct air capture condition, which is exposed to the surface of the fiber, worked the best because there's no mass transfer limitation. Everything was on the surface. But all these materials are not so bad either. So we got really excited about CO2 capture using encapsulated in fibers. But next 10 minutes or so, I want to talk about something else because we're still talking about carbon capture, catch and release, and hopefully you will compress and send it to somewhere for either storage or utilization. But what if we combine these into one system? That's what we start thinking about. So there are many different ways to convert CO2 to valuable high energy materials or valuable materials like a CO or plastics, polymers, and formic acid and all that. One of the ways, and Jing is working on that a little bit, is the electrochemical reduction of CO2. So if you look at the electrochemical reduction of CO2 to valuable chemicals and fuels, there are many studies they've been doing about 15, 17 years of really active research in this area. Most of the research was in catalysis. Like somehow, if I have a CO2 delivered to the surface of the catalyst, their catalyst can actually make good stuff. So then there's a catalyst composition, surface, morphology. All these are really important research. And in fact, if you're using silver catalyst or other catalysts, they usually make CO. But if you want to make more than C1, C2 plus compound, bigger carbon-bearing chemicals and materials, you need to go to copper. And copper has to be very spiky. So knowing that, I was curious about, well, you just assume somehow or another CO2 will show up to your surface of a catalyst. But how are you going to get there? Because a lot of electrochemical systems use electrolyte, which is water-based. But CO2 solubility in water is not good. That's why we don't use water to capture CO2, right? So you paid a lot of energy to capture CO2 into pure form, and you try to bubble CO2 into the electrolyte, has very poor solubility of CO2. Okay, now you have two solutions. Either get rid of all that water and go through gas diffusion electrode. That's one route a lot of electrochemists went into. Or maybe you can design your electrolyte to have a higher solubility of CO2. So of course, I went to that route because I love materials design. So we looked into how to design or develop better electrolytes. So let's think about very simple system. Two fluid system. One is with the NOMs, the other one with the polymer, which is untethered. So this is tethered, same polymer here, same polymer here. Major difference is that this one has nanoparticle, this one doesn't. The polymer here is untethered, this one is more structured by bound to the surface. That's the only difference. So looking at that, I thought, if this solution behaves as well as this, close to that as electrolyte during the CO2 reduction, I would love it. Because having all these nanoparticles, inorganic materials, I thought this should have a higher viscosity and lower conductivity. That kind of makes sense, right? So I send my students to the lab and then they keep doing experiments. And this is data he brought back. And then this is the PEI-based one. This is NOM-based PEI. Somehow or another, it had a higher conductivity and lower viscosity with NOMs-based electrolyte. So I was getting so confused, like why? Because there's a polymer that's kind of stuck to the surface. It doesn't really make sense. So we keep going back and forth, back and forth. And I realized maybe something's happening inside, which I didn't anticipate. So we actually took this to Argonne National Lab. And if you're familiar with USEX, this is not SAX, USEX data, that Q is inverse of the length scale. So whenever you work with nanoscale materials, you have a lot of signal at the high Q range because that's nanoscale materials. Usually you don't get signals at the low Q range, which is chunkier stuff. But as you can see, we have much of the chunkier stuff. So what we realized was on our naked eye, this material is a very clear solution. Looks very clear. But if you zoom in, there's agglomerates, even micron scale. If you even zoom in further, there's like a tens to 100 nanometer scale aggregates. And then because of that, the interaction between one NOMS to another NOMS was very different than what we anticipated. So then there was a lot of channeling happening, very different transport mechanism throughout this fluid with a hierarchical structure. So obviously we can do something. And we even took it with our Mark Dodman, our friend at Oak Ridge National Lab. he did the SENS, which is the small angle neutron scattering. And what he also found was, we thought that all the polymers are really well tethered onto nanoparticle. That's what we thought. Because when we do TGA, all these polymer degrades at the same temperature. So we thought we have a single type of polymer tethered onto nanoparticles. That's what we thought. But this SENS data basically showed you there are two types of polymers. In fact, two polymers tethered and there's polymer in between. Now we call this interacting polymers. They never, it's so stuck in between polymers, it doesn't come out to the bulk. But then depending on the local reaction environment, it kind of opens up and closes down. And by doing so, it was changing the hydrodynamic behaviors and interaction with the fluid molecules and gnomes so that it was changing the way how it has a transport behavior in this electrolysis. So now we can design really interesting new electrolyte for CO2 capture and conversion. So if you look at the data, this is the just water-based electrolyte. CO2 capture is very tiny. In fact, if you look at a lot of data for CO2 reduction, electrochemical reduction data, they start with this concentration. Even then, Herpes conversion was very low at the time. Now your catalysts are getting better, you will be running out of a CO2 to convert. So now if you add more gnomes, you have a huge increase in CO2 concentration on your electrolyte. This is great. And in fact, if you're using chemisorption, in this case, you can put a lot more CO2 and also conductivity goes up because you start making carbamate and sometimes even bicarbonate. So we got excited. So let's convert this absorbed CO2 in this electrolyte into something useful. So this is a typical data using silver. We got it from Feng Zhao's group, who's another buddy of ours in energy and fuels. And this is showing that we can make hydrogen, the CO from CO2, and competing reaction is a hydrogen evolution reaction. So depending on the potential, you will make some hydrogen here. Very typical data. But if you do gnome-based electrolyte, it looks like this. Very different here, a little bit similar to first one, right? So this is a phase-dissolved CO2 in gnomes with ether groups. So there is an interaction. CO2 capture is done by weak Lewis acid-base interaction with ether groups, compared to this is when you really made carbamate. So what happens is that when you make carbamate is not electrochemically active. So only a tiny of the CO we made was just a phases of CO2 in the solution. That's all we were doing. But if you have ether groups, it's a weak enough binding energy, you can start to convert quite a bit of CO2 to CO. So the way you can convert carbamate into CO, you actually have to run your electrochemical cell at 60 degrees or higher. Then you start to thermally regenerate your material, release that CO2 locally, and you can start to convert that CO2. So we start looking at the Faraday efficiency. If you're not familiar with electrochemical reactions, this Faraday efficiency is basically telling you selectivity towards a certain product. So if you look at compared here versus here, it's not exactly the same. So we start to think that, well, somehow or another, although we use exactly same catalyst, it wasn't going through exactly same reaction pathway. So in fact, if you look at what gnomes is doing in the system, it can deliver CO2 to the bulk and release that CO2, especially if there's gnomes with ether groups, and that release that CO2 will be phase-dissolved onto the surface of the catalyst. In that case, your Faraday efficiency should not change, right? Current density might be, but not Faraday efficiency. But we did change the Faraday efficiency, which means that some cases, gnomes actually deliver CO2 to the surface, even the ether group ones. And then what happens is at the surface of the catalyst, when CO2 gets absorbed to the catalyst, the ether group surrounding it was bending CO2 just a little bit and changing the way it was reacting. So now we can start calling it maybe as a co-catalyst. So there's a lot of design we can do. So now you can see that bulk measurement is important, but actual measurement really, really important is at the interface, electrode-electrolyte interface. So we went to another friend of mine at NREL, National Renewable Energy Lab, and Wilson Smith has really interesting AFM system. This AFM system is not only looking at the topology, but they also can do EC. they can do electrochemical reaction while looking at the topology. I thought it was really cool. So then what we did was started with very simple silver foil, right? This is the electrode we can assume. And let's look at the two systems. One is silver foil with water above. One is silver foil with the PEI solution. I didn't apply the potential, nothing, just looking at the topology. So as you can see, there was a little bit of difference in modulus and deformation, because if you have a selected absorption of polymer onto surface of the silver foil, it gets squishier, right? So by looking at the deformation and or modulus, you can kind of tell, was there absorption, selective absorption of a polymer onto surface of any surface, especially electrode. So we were looking at that. So now what I was really interested in is what would happen to the layer during the applying potential. That's the when we're actually doing the reaction. So let's start with a very simple system of PEI solution. There's no CO2. I haven't bubbled any CO2. There's no supporting electrolyte. As you can see, the no applied potential, there's some number we can get with the topology. And now let's apply the potential. And then what we saw was that the grafting or the amount of polymer we added, all the polymers start to collapse onto the surface. So that its stiffness on the surface got really different, right? It was a lot stiffer with this versus this. There was a transport behavior will be very different. What is on the surface in terms of CO2 will be very different. So then now we wanted to see what if we bubble CO2 and have supporting electrolyte. This is really mimicking our CO2 reduction reactor, right? And then we wanted to see what would happen if we apply the potential. And this is what happened. In fact, all the carbamate ions and bicarbonate ions and supporting electrolyte let this polymer stand out still. So that it was very different than what we expected. So using just a typical AFM would not give us this information. Now we have to really develop more tools to understand why we are doing electrochemical reaction, what's really happening on the surface. For example, what would be the real pH condition? Measuring bulk, not going to give you a real micro environment of what's the pH condition, what is the form of CO2 at the interface. So these are the things we've been working on. There's a lot of interesting things that are happening. But last 5-10 minutes or so, I want to kind of wrap up with the clean energy transition discussion. This is one of the areas even this current government in DOE loves. And I've been working in this area not because funding. It was more I was curious about from one of my another research area, carbon mineralization. I thought, well, let's look at what's happening with clean energy transition, because people keep thinking that don't do carbon management. We just need to have more solar and wind. Having more solar and wind, is it really clean energy transition? That's a big question. So I start asking that question. And in fact, Department of Energy start asking that question a number of years ago. I think it was almost 7-8 years ago, they start having this map of things. They said, in order for us to go to clean energy transition, including batteries and solar and wind, we need a lot of rare earth elements. Where does it come from? Right? I started asking these questions. And in fact, they're going beyond REEs, rare earth elements, so that there's now called energy relevant critical minerals, and that includes all the rare earth, lithium, nickel, cobalt, even copper. You need all of those. So then I started looking into this area. Sounds like mining, right? So I started looking into mining a little bit. How many of you been to Bingham Canyon mine, copper mine in Utah? I've never been to. I wish I can. One day, this is a big truck, and then there's a little tire, right? This tire is twice taller than me or even beyond. It's a huge system. It's huge, huge, huge. Okay, look at this, the man-made structure of mine site. This is one of the biggest man-made structures so that you can see from space. It's a huge. This is what I'm used to. This is called serpentine. This is magnesium silicate minerals. They used to mine for nickel. And then after get some nickel out, and then all the mine tailings are sitting around. And this is the material you can fix carbon dioxide and then make into magnesium carbonate. So this is one area I've been working on for a long time. Waste with another waste and then making into something neutral, store carbon for a long time. So I started looking at this and I go, well, we need a lot of copper apparently to have more EVs and solar PV and all that wind. So what do you think? Let's think about something easy. Like everybody has cell phone, right? How about how much copper you think we have in our cell phone? I didn't know. So I asked Google. I should ask ChatGPT now, right? According to Google, it's about 15-16%. In average, right? You need to connect a lot of things. And if you look at batteries, it has a lot of nickel in it, right? So let's look at where these copper and nickel actually came from, which is here and here. What is the concentration of copper in this ore? Let's guess. So if I have two rocks, and I can call one rock and with the other one ore, only difference is it looks exactly the same to me, at least anyway. Only difference is that this one has enough copper to be valuable. That's the only difference. Okay, what do you think this copper ore is, copper concentration? 10%. 10%. 0.4%. Isn't it crazy? We complain about direct air capture because it's 400 ppm. Apparently, we go to something has only 0.4%, 4%, and we actually move the mountain every day, grinding up like crazy, and then take only fraction of that 0.44% and leave everything like this. Nickel ore used to be good ore, used to be 2%. Now all those we already mined is a 0.2%. So clean energy transition actually is more mining. Okay. How many of you love mining? We don't like climate change, but we don't like mining either, because the mining to us is a more environmental footprint. But the thing is, we don't see this in our backyard. So driving Tesla, you think that, oh, I'm doing good for the environment, right? So can we stop mining and still do clean energy transition? Not likely. So which means that we need to come up with something. I used to call it sustainable mining. They don't like that word, so now they call it resilient mining. Whatever you call it, I don't care. At the end of the day, we need these resources with a minimum environmental footprint. I think that's very important. So one of the companies I work with at Tamarack, Minnesota, Rio Tinto has really good site. This is my ARPA-E grant, one of the projects. And when I went there to visit, because they have a good nickel mine, there is a lot of Tesla running around with this bumper sticker. It said they have carbon neutral nickel in this Tesla. I don't know whether it's true, but at least it's a bumper sticker. So then what they're saying is they're going to do carbon sequestration while getting as much nickel as possible. That's what they're claiming in this site, and that's what we are working on right now. But one of the challenges when you try to do this, taking more nickel out of that, remember nickel was only 0.2% of the rock. Tiny fraction. So then now you're going to process the entire rock, because not only you're going to get to nickel, fraction of nickel, you're going to also do carbon sequestration, meaning that you want to get all the metal out, not only tiny bit. It becomes very challenging separation problem. Because now you need to get the nickel out when there's a lot of magnesium in the solution or calcium in the solution, many competing ions. So now you're not doing separation the same way. You're not doing flotation. You might do some, but a little bit. You're going to be digesting entire rock so that there's nothing like this sitting there, right? Because the entire thing will be digested. We're going to be sequestering carbon and taking as much nickel as possible. Okay, so then I thought, well, the separation challenge is very interesting. Can we do something? Because can we design a material can get to the target metal in the high concentration of competing metal ions? So we went to biology. If you look at some, for example, the system with all these functional groups, biology does cerium capture, for example, with many binding sites so that you really grab onto it. And in order to do that, they create a cavity just right size for cerium. So what I decided to do was, why don't we develop something called structural ligand system? So we have backbone of scaffold, and then put the ligand right location so that create the right size cavity with the multidentate binding at right locations. So we start doing, well, can we capture cerium, because we are modeling after that biological system, in the high concentration of calcium and magnesium, can we grab onto only cerium? So here's some of the data I will show you. Without going through too much detail, you can change the functional groups to change the basicity of your functional groups. You can do a lot of things. So data here, cerium only, cerium against with the sodium, calcium, and magnesium. Data doesn't change much, right? we were able to somehow grab onto cerium in the presence of a whole bunch of other ions surrounding it. The reason was, this is our DFT calculation, because the tiny size difference, the cerium was really snug to all 7 binding sites compared to calcium and magnesium. It doesn't bind to all the sites. So it was kind of bouncing in and out of that space so that we were able to capture only cerium. But remember, I was telling you earlier time that any separation technology is catch and release and catch and release, right? We want to use this material many, many, many times. So if you look at the catch and release, it's done by some kind of energy, in this case, chemical energy of a pH swing. So binding on is a pH 8 and up, you will bind all the metals. And then if you lower the pH to 4, you will release. In fact, in the mining industry, it's called liquid extraction. So in order to do liquid extraction, you put a lot of ligands and these collectors, and then it moves all the metal ions into organic phase. Once you get the organic phase loaded with metal, you put strong acid in to do acid wash. Then your metals comes out with acid. That's what you do. As you can see, this is not environmentally friendly system at all. So when we designed this system, we really want to make pH range just right here. If you work on CO2, you should know why we are targeting this and why we are excited about it. Because this is the CO2 hydration, right? So what we are proposing to do was we bind metal at pH 8. If you bubble CO2, you lower the pH, we cannot ever go down below 4, right? So we can go down here and release all the metal. And then we just need to bubble air to degas all the CO2, get more neutral pH, then we were able to restructure all the structural ligand. So let's test that, and then this is the data. So this is the pH 1. This is typically what conventional mining people do. So put the pH 1 or even lower strong acid on the system, then you crash out all the metal, recover 92 plus whatever percent. If you do pH 3, we're trying to mimicking the bubbling CO2 system. You can see that there's only little 40% or 35% metal comes out, right? Which is expected, right? But then when we bubble CO2, pH only went down to 4 to 5. But we recovered 94% more than the strong acid case. We were recovering most of the metal. So we're like, oh, confused. Why? It was super excited, but I was like, what's going on? And this isn't what happening if my screen only showed me this figure. And I'm confused, right? It's like, why? It's weird. So then I finally went into the lab to see, like, why is happening? And then she showed me these 3 beakers. Now I know why. She didn't tell me this was cloudy, right? What happened was, when you bubble CO2, we were making cerium carbonate. So by doing the precipitation in the water phase, we keep pulling more metal out of the organic phase. So even at really mild pH condition, we were able to recover all the cerium we wanted. So which means that if we can do liquid extraction with the minimum pH swing, you can do PCO2, partial pressure CO2 swing, you can get their very green chemistry. If you can make any metal to precipitate out, then you will do really well even at medium pH conditions. So I don't know whether it's really carbon neutral. Hopefully we'll get there together. But there are bigger questions that people were asking in our area CCU especially. You can make jet fuel from captured CO2 and green hydrogen or blue hydrogen, whatever carbon-free hydrogen and renewable energy, and we can make jet fuel. People did talk about a SAF, right? Sustainable aviation fuel. Or you can get jet fuel the way we do it from crude oil. Okay, which one is better for the environment? It's similar to paper cup versus plastic cup. And Volker is here, he will answer that question very well, right? So unfortunately, a lot of materials, if you have a cup of like a soda, you can tell like there will be a calorie value. There's a calorie, it doesn't matter whether it was made in Michigan or LA or New York, it'll be same calorie as long as we use same recipe. Carbon footprint, we cannot ever print. You need to know it's a path dependent, every step of the way, which water was used, which CO2 was used, which bottle was used. It's very hard to pinpoint. So I think the good sign is with all the AI machine learning, maybe we can do more good data management so that we can really fully evaluate what is the actual environmental footprint of any of these materials we are making. So overall, we need to do it all. I don't think there's a one winner gonna solve the ore problem. I think we need to consider all the CO2 sources and all different pathways to store and utilize. And the future, especially for engineers, I think we really need to think about electrification and reactive separation for the future. Our society, including University of Michigan, New York City, LA, we blessed with high energy density fossil resources. Without that, we don't have any of these. That's the truth, right? That was interesting because our energy source had carbon and hydrogen embedded inside. That's an amazing thing we had. But now, if I'm telling you that we're going to give you renewable energy, which is in electron, you need to figure out where you're going to get hydrogen and carbon. And that decoupling makes it very complicated how to put everything together for the future. And I hope that we'll create the new pathways to existing materials and chemicals. But let's think about how to create the new chemicals for the future. Because if we are starting from carbon dioxide compared to fossil, which is very reduced form, if you're starting with either CO2 or biomass, very oxidized form, if we are only thinking about functionality, should we make the same stuff as a commodity chemical? It's a big question. And whatever you do, hopefully you put environment, human within your system boundary. Here are my funding agencies and my wonderful students, and I will be happy to answer any questions. Thank you.
Would you manage answering questions? Are you watching the chat? So if you're joining us online, please either just chime in or put in a question in chat. But questions? I can see one real quick.
Sure.
The Petronova plant. So they use the captured CO2 in historic recovery.
Yes.
What's the benefit on carbon if I'm going to use the carbon dioxide I've spent all that energy to capture to produce more fossil fuel? That would not look very good on a carbon balance if you
No,
look
it
at it
doesn't.
overall.
So that's not the question. It's not about net fossil use. If you do that, it will be never good, because if you're putting more CO2 in and you take only a little bit oil out, your EOR system is performing very poorly. That's not what you want to do. So you do enhanced oil recovery to get as much petroleum, crude oil out as possible from each reservoir, and you should do well if you want to. So the competition or comparison you should do is that if you're doing regular EOR versus the capture CO2 EOR, today, unfortunately, we still do EOR, and those are not the CO2 we capture. We actually mine carbon dioxide out of the ground, which is well stored by Mother Earth to do EOR. So that comparison, if this looks good, should we continue to do it? No.
Could you have improved the energy balance? I've heard the same exact ratio. They were looking at building, Duke Energy was going to build a complete CCUS power plant outside of Pittsburgh. And they're going to have to build a 3 gigawatt power plant to end up net with a 2 gigawatt power plant. If you used, as our colleague Rohini Balachandran is very interested in, solar intensified energy to do some of the thermal processing in that plant, could you have made that total energy demand better?
I'm sure. I mean, if we can use any of the integration of solar energy and then you maximize CO2 storage, you can, but you have to optimize or make sure that you don't take too much carbon out of the ground. So your oil reservoir not going to be operating at maximum capacity. It should, depending on how much solar you have and how much storage capacity you have. You can manage that. And in fact, a lot of people think that that's a better way. So one thing people don't understand is that here, they think that there's a single reactor, you put CO2 in, hydrogen in, and like a renewable energy, you make wonderful sustainable aviation fuel in single step. That reactor, usually Fischer-Tropsch reactor, like you need to convert CO2 to CO, and then you add CO to hydrogen and then into Fischer-Tropsch reactor, comes out as crude. It looks just like this one. And then you have to do distillation, and so there's a lot of process goes into that. So it's not as simple. There are now, if you don't need to do jet fuel is a complicated hydrocarbon mixture. But if you can have much simpler hydrocarbon, that is okay. You can do that single step. But the fact that you're making crude out of this single step, or not even a single step because you need to convert this one already. So it gets complicated very quickly. So doing the energy calculation is very important. And what scale up can we do?
Thank you for a wonderful talk. Just wondering, with the CO2 bubbling for the weakly acidic extract from the metals, I just wondered if you or anybody else had looked at sort of the scalability of that, any LTAs or TAs that have been done on that?
No, we just started. I don't think that this one will be very hard to scale up because it's just bubbling reactor, and liquid extraction has been commercialized for decades, so it's old technology. The biggest part, in my opinion, right now I'm just still doing liquid extraction, organic layer and water layer, right? You're doing that. But I think the best innovation, which I just submitted a proposal on, is if we can get rid of the entire organic layer. Patent pending, so I cannot tell you, but it would be amazing if we can do that. So I think there are a lot of things you can do. Bubbling CO2 back and forth is done before. It's not like that's difficult, but people did not do it because they didn't have a ligand operates at this window. So if you look at the binding on and off, a lot of these liquid extraction ligands, they bind here, but they won't release until pH 1. That's why we can use it. So we were looking for ligand, structural ligand, which open up just a little bit at the minimum pH. That's what we are looking for. So it's not the most effective one, but greener one.
Yeah. For your beautiful polymer material, how to characterize like a single norm? Single norm.
What do you mean?
I see like your scheme show like a single norm. How do you know?
Oh, I didn't do single norm. No, because
No.
it's tiny. So what happens is that I purchased the nanoparticle. So because I want narrow size distribution as possible, so I get the silica nanoparticle, which is like either 7 nanometer or as big as 21. We use a very similar one, so whatever data we get will be very clean. So we still measure the bulk. We don't do one at a time.
Okay.
But because we use very narrow size distribution of the nanoparticle, we can get very clean data.
You're very clear.
I have a question. Is the direct air capture plant that you mentioned, the one that you visited, it says that it like it converts like to produce 1 megaton of like CO2 per year. But then how much like kilograms of coal or whatever like input that you're putting in for the energy source? So like efficiency
Good
wise,
question.
is it saving more than it's?
Good question. So in fact, it was really funny because I don't think the picture. Where are you? Okay, so this one, you know where it sits on? It's a waste to energy plant. It's sitting on top. So I think they have increased the CO2 concentration. Don't get me. But they actually use their waste heat to do their system. So in fact, when you calculate life cycle analysis, even in the power plant regular CO2 capture system, because we are using waste heat, you don't put any additional, you don't have additional carbon emission because you're just using waste heat. That was the whole decision. So here they put it on top of, I think it's waste to energy plant, and then they cannot go from 400 ppm all the way to 100% CO2, but they can usually go 400 ppm to about 15 volume percent. So actually they pipe CO2, ambient pressure, it get very close, it's not compressed, send it to greenhouse. Greenhouse loves elevated concentration CO2. So, but this becomes very interesting question. Why would you put this on top of a power plant? Because the one good thing about people could keep arguing is that direct air capture, you can build it anywhere. Is it true? Not always true, but they were saying, oh, we can build direct air capture unit on top of a reservoir where we want to do geological sequestration, then we need to do piping. Like CO2 pipeline is very, very expensive and policy-wise really hard to get approved across the different states. It's complicated stuff. So they were saying, oh, we just need to do direct air capture above the reservoir. That's not easy either. But let's say we did that on top of the reservoir, and then you have direct air capture system, huge farm of it. Where would you get energy? There's no waste heat to do regeneration. So then let's say it's off grid, there's nothing near, we can use waste heat. What is the easiest energy for you to provide tomorrow? Solar. Solar is cheap. You can buy it on Amazon and then say, okay, I'm gonna put solar PV everywhere, you plug it in, right? So that becomes interesting because solar PV gives you, or wind, or whatever is in the off-grid, gives you electricity, electron, not heat. So then how would you regenerate your material with electricity? Well, you can get electrical blanket and then put it over. It's not very efficient, right? So people start thinking about, okay, now we need to think about, again, similar to electrification of anything. We need to think about non-thermal energy transfer to do what we want to do. So when you have a materials, at the end of the day, chemical engineers like me and mechanical engineers too, we love steady state process, isothermal reactors, right? So that you will have capture reactor and regeneration reactor operates a very different temperature. This one will be ambient temperature if it is direct air capture. The regeneration reactor will be operating at 120, 140 degrees C. Means that this entire reactor wall, inside, sorbent material, everything has to be 120, 140 degrees C. But that's maximum energy penalty in a sense, right? Because you don't want to heat up all these things. So we start thinking that if we can just zap and send remotely energy to where carbamate is, and just enough to break the bond, that will be best, right? Because then your capture reactor and release reactor will operate exactly same temperature. Of course, this is theoretical, right? Minimum energy. So then people started thinking about what are the non-thermal energy transfer method. I think we've been working in this area 6-7 years in the United States. You can do easiest one. You use it all the time to heat up your food at home. Microwave. So you can do microwave. Some people use joule heating. A lot of people at Stanford using that. I think Arun Majumdar just published a while back with Jonathan Van. There are many other techniques, plasma. So people are looking at that, but still, nobody really done LCMTA well yet. I don't think so, because if you look at household microwave, it was designed to create a lot of friction for water molecules. So do you really want to activate water molecules or something else? You need to really target for right molecules. Another thing is that we don't really care about energy loss. We just want food to be heated up quickly. Right? Another thing is that you see when you put your food in microwave, it rotates, right? Because standing wave, if you don't rotate, certain part of food get really hot, certain part doesn't get heat up because standing wave and it's a long, right? High frequency. So you really need to think about how to design the reactor better. I don't think we know that yet. So one thing we know is that, for example, my group been working on microwave reactor, next generation of it. Definitely, we can release CO2 instead of half an hour to an hour, within a couple of minutes, all the CO2 comes out. And surface temperature of particle or fiber remains very cool. It's about 50 to 60 degrees C, but we still don't have a method to measure molecular level temperature difference. I think that where carbamate is much higher temperature, but I don't know how to measure that, right? So that's another challenge, but we're just guessing that. So we know kinetic is much faster. We are targeting heating and all good. But at the end of the day, 100 units of a microwave energy renewable energy gone into microwave reactor, how much of that went into releasing the pressure, the CO2, we do not know. So for example, we love to get joule, how many joule per mole of CO2 release. I don't think there's any publication on that yet, just because we don't have good method to measure that yet. But there are a lot of interesting areas going in, and in fact, because of that, I think we should think about how to evaluate these much different ways for the future to really know the benefit.
Well, let's thank Professor Park.